Hello, my name is Rhys, and I'm going to talk to you about how you can use state in an AWS Lambda. So a little bit more about me. I work as a principal engineer at the Financial Times, and I'm a principal engineer in the reliability engineering team. And I used to have a lot less hair. So this is ft2.com. It's the Financial Times' flagship product. It's an award-winning news website, and somewhat controversially, we both make a profit and publish the news based on the facts. It's not the only thing we run. This is FT China, and we've got a host of other business and finance websites, plus lots of internal tools. And we also publish a newspaper 6 days a week. So all this relies on a lot of technology. And one of the jobs of my team is to produce ultra reliable runbooks for all this technology. So the way we've architected that is we have an S3 static site in 2 different AWS regions. In front of these, we have some Lambdas, which carry out the authentication. And in front of that, we use the Fastly CDN, which automatically fails over between the regions if something goes wrong in one of them. And that is able to detect the health of the stack in any given region, because we run some other Lambdas which are constantly checking the health of this underlying system. So the attractions of using that architecture, or what's the point, introducing Lambda into it, was it's operationally a bit simpler, but also supposedly a bit cheaper, because this site, it's maybe gets a couple of 100 page views a day at tops. It has to be available, but it's not very used. So Lambda seems like a very cheap option for that. However, when you've got, I think Fastly have about 50 points of presence, when you have them pinging our health endpoints every 5 seconds from all these different regions, that can quickly add up. So this is a back of envelope calculation. It's actually slightly wrong. At the peak, we were spending $400 a month on this, which, yeah, again, it's not gonna break the bank, but we expected it to be pennies, so that's not great. But I'm a Node.js programmer. I used to specialize in performance, so there are various patterns you can apply. You can throttle functions to avoid avoid too much computing needing to go on. There's a pattern called the long polling pattern, which I'll go into in a bit later. You can use in-memory caching, use fire and forget, so you can make a request and only wait for what you need. So what I'm going to talk to you today about is how and why these approaches succeed when working in a Lambda, and also what they teach us about how state works in a Node.js Lambda, because it's not entirely obvious, it's not well documented really. So this is the program. I'll tell you about what kind of states you can use successfully in a Lambda. Then I'll tell you 2 stories about when things went wrong for us. So this is taken from the AWS documentation, or it might be the marketing site, I'm not too sure. So while AWS Lambda's program model is stateless, your code can access stateful data by calling other web services such as Amazon S3 or Amazon DynamoDB. So that kind of suggests that there's no such thing as state in a Lambda. Every invocation is completely independent. You don't have access to any shared stuff. But that's not really true. So through watching this talk, which is at reInvent last year or the year before, plus some educated guesses based on what I know about Node.js and working with Lambda, these are some conclusions I've made about using state. So first of all, a Lambda may reuse a worker process once it's been set up. Reuse that for multiple invocations. That's what it means to not have a cold start. So it means your process is primed and ready to go. So what can we learn about state from that? So Node.js, a module, is just a collection of stuff. So it'll be variables, functions, classes, what have you. And they are held in memory. And the Node.js process is a load of modules, all referencing each other, plus the Node.js runtime. So if that process is reused by each Lambda invocation within the same worker, that must mean that that state in those modules is also preserved between invocations, because otherwise you're not really using the same process, because they're a completely essential part of that process is the state stored in those variables. But it's not special, that state. It really is just normal variables. It doesn't matter that they were created on a startup. That's just incidental. So it really looks like we can share state between invocations just by using variables, which is pretty much the same as running a persistent server. Now, there are some caveats to this. Your event going to Lambda might be the first one it's handling, so not everything may have been set up yet. So before you assume some variable has some state in it, check that it does. And also, if you've got multiple worker containers running lots of copies of your function, the data won't be shared between those different workers. But that sort of thing is true of any containerized architecture, anything where you scale horizontally. So it's not really a special caveat for Lambda. I mean, looking at this, it seems obvious that while AWS would obviously love you to spend all your money on Dynamo and Redis and other stateful services, you can actually stick stuff in memory and cache it between requests, and that will work in Lambda. So yeah, you can write your code in your Lambdas and treat them just as if they are ordinary servers, and nothing will go wrong. But of course, things can go wrong. So yeah, I've just told you about what works reliably, using variables and expecting them to still be there between invocations. That works. No problems with that at all. But there are some quite similar things which don't work. So the long polling pattern is a favorite of mine. If you've got a resource which will be used in much the same way to handle multiple client requests, you can fetch that resource, store it in memory, and then use it between lots of different requests coming in, which saves having to fetch it every time, so that makes it faster and it makes it more reliable. So in this example, the Lambdas, which were checking the health of the application, they would run a job basically checking that you could fetch a page successfully and authenticate. They do that every few seconds, store the result of that in memory. Then when this storm of requests were coming in from all the Fastly points of presence probing the application, that one result was shared between all of them, which has saved us a lot of compute time. Now this is an example of roughly the structure of that. So we've got something that fetches a resource, does some work, that is being run on an interval of 5 seconds, sticks the result in a cache object, which just for this demo purposes, we're using an array. And then you've got the handler, which also does some work, but it also, as well as the result of that work, it returns the objects in the cache. And I wrote a script which runs that multiple times, constantly getting slower with a longer gap between them. And this is the result of that. So you can see you start off with nothing in the cache, and the cache gradually gets filled up, and everything just works. So that essentially works very similar to how you'd expect it to work in a normal server. All good. And what if I make this change? This hasn't touched anything about that cache, but if we were doing this talk live, I'd probably ask for hands up to see if you can guess what happens. Well, this happens. Initially, nothing gets put in the cache at all. Then after a while, you start to get these errors. And still nothing really is being put in the cache. The reason the cache size is going up is because we're starting to put errors into there. So what is this error? Econ reset. So the reason this is happening is because previously the handler was staying, had some work to do, so that meant the process was staying alive for long enough, those background requests, to at least some of the time, in fact most of the time, get handled successfully. Whereas now, without this work, this handler executes more or less immediately. It happens on the next tick. So that means this background job just never gets a look in. It will never finish. So after a time, resources elsewhere in the Lambda stack get a bit tired of waiting, and the connection is closed. And I mentioned there that there's things elsewhere in the stack. We had, when this went wrong about a year ago, it was very confusing to debug because some of the errors were coming sort of outside of Lambda invocations. We were getting some really weird, difficult to debug things. So when it does go wrong, it's horrible. And I think we can learn from this is that in some ways, a Lambda really isn't like a server. And those ways do not always surface themselves. So you can treat your Lambda like a server for a really long time, and then suddenly you'll break because you've changed something. Like in this case, we made a change in the handler. We didn't change the caching mechanism at all, and yet the caching mechanism is broken because of the way the Lambda architecture executes your code. So you can get this false sense of security that it cares about your code. In general, though, polling and other background tasks won't work reliably ever. They may seem to for a little while or under some kind of test conditions, but in general, background tasks don't work in Lambda. What you can do instead, if you want to do some kind of background updating thing or put stuff in a memory cache, you can have a cache that when you fetch a resource, you put it in the cache and otherwise fetch it from the cache. And some job which returns a promise, which cleans out the cache for items that you don't want anymore. So then you can kind of flush the cache, do the useful work that you wanted to do, and as long as you wait for the cache cleanup to finish before returning, then this will always get time to execute properly and your cache will work. Now, if a word of warning about third-party libraries, that even quite simple things like LRU cache is a very popular caching library for Node. So it says it deletes the least recently used items. We can't actually tell there if that's going to be Lambda compatible. It might be the case that when you run it in a Lambda, it's never able to clear out its old items because it does some background work. So be careful using third-party libraries because they might demonstrate similar things to the bug that I just demonstrated, and it won't be obvious that it's there. So next, another interesting, nice bug we had. So this is roughly what our health checks look like, stripping out all the other efficiency patterns. We are fetching a URL. If it returns an OK status, we return 200, otherwise a 500. After a while of running this, we started getting this error: n file, too many open files. So what does this mean? Well, it's a system error, and it means the process has run out of pointers it can use to open files. The Lambda containers, they have a limit of 1,024 file pointers. So that's as many files as your process is allowed to open. Now, a TCP socket, for reasons I don't know, also counts against that balance. So what was actually happening was we had too many sockets open for HTTP connections, and we were blowing that limit. Now this, taken from the talk I referenced earlier, is a rough picture of the Lambda architecture. Now up here in your code, that's what you control. Everything else in this big stack is controlled by AWS. And no abstraction is perfect. And occasionally the stuff that lies outside of your code base leaks out. So some things about the Lambda Lifecycle. The container that it's running in is released for reuse when two things are true. When the callback is called, so basically your handler has finished running. And secondly, that there's nothing left on the callback queue. So there's two reasonably familiar concepts. But Node has quite an interesting architecture, and that's built on top of a load of C libraries. And whenever these C libraries do something, they kind of fire an event in the event loop, which will then in turn take control of calling the appropriate callbacks in Node. So as an example, when you read a file using a stream, a readable stream instance is created. And in your process, you can attach callbacks to the various events of that. And then when the C library that actually does the reading of the file changes its state, it will trigger an event in the event loop, which then calls the callback in the Node.js process. And this is true for most kind of I/O operations, I think, in Node. So if you call it the read file operation, that's just a shorthand for streaming all the data and then waiting for the on-end event. So it's still a bit of a mystery of how this would blow the limit. It's, again, if we were doing this live, I'd be asking for people to guess. I don't think it's obvious at all. So this is what happens when you send a GET request to the Fetch API using Node Fetch. It wraps some Node.js core HTTP library and returns a stream. This in turn is built on top of the underlying LL HTTP C library, and there's a socket opened. But as soon as enough data has come back to serve the OK status and the headers, that initial callback attached with the promise is resolved. So once we get to here, we've got the OK status just on the first fetch promise. But then, because it's a get, we're asking the system to get us the entire body. So the socket stays open, waiting to download the body, but we haven't actually attached any callbacks to that. So there's no event listeners. So our function is returned. And also we don't have any listeners waiting. So the container is released for another invocation. So this is roughly what's going on. We invoke the function, it opens a socket, and it stays open even after the Node.js process has been exited. It keeps happening until eventually we blow that limit. So I couldn't actually recreate this bug for this talk. This happened about a year ago, and possibly there's been some bug fixes somewhere in Node Fetch, or maybe in Node, or in Lambda, or possibly it does still happen, but I just can't remember the exact conditions. Anyway, but I still think it's interesting because it's a good example of where the stuff outside your Node.js process going on within the container matters when you don't really have much control over when the Node.js process runs or not. It's an example of where Lambda is supposed to remove, sort of abstract away the running of the server, but still you are in a server, and that can still sometimes affect you. So the lesson from this is to make sure you always clean up after yourself whenever you reach outside of the Node process. For fetch in particular, you can use the abort controller library, which allows you to forcibly close the socket early. And another sort of parallel point to this is Lambdas have limits. It's not just the memory limit and the timeout limit. There are lots of others. So we've hit all of these, the file descriptors, just told you about that. Not so long ago, we hit the storage limit when we were making a zip file as a backup. And there's others as well. So in conclusion, Lambda is not as stateless as you might think. It's still a process running on a server. AWS do a good job of abstracting away and managing that for you, but you can never get away from it completely. So this has some upsides. So it means you can use variables and use state in a far more wider sense than the AWS blurb would like you to. In particular, you can do in-memory caching, but you need to be careful that it's implemented the right way. In general, it's not safe to do anything async unless you wait for it to complete. No background jobs. They will fail eventually. But this also applies to kind of hidden things you may have kicked off outside the Node.js process, which you don't realize you've created. So yeah, there's some dangers hidden there. So if those two sort of rules of thumb, even if you break them, Lambda may seem okay for a long time, but it's trying to trick you. Don't trust it. Stick to the rules. Thank you.